3 proofs of the Pythagorean theorem. Let's start. What is the Pythagorean theorem? It's basically a theorem that says that if we have a right triangle, so one of the angles is 90 degrees, then we have side A, side B, and side C. It basically states that a squared plus b squared equals c squared. So now we're going to prove this in 3 ways. The first proof is going to be sort of a classic proof that you can see on YouTube all the time. The second proof is going to be Einstein's proof that he made when he was 12 years old. And the third proof is going to be one using calculus. Let's start with proof 1. I'm first going to build a square. Okay, so that's about a square. So here, let's label these sides now. This will be A, B. A, B, A, B, A, B. And from our notation, we have that these sides are going to be C. Because this is a square, all of these are right triangles. Okay, and these are all similar triangles because they have the same sides. So that means this is one angle, and this is the second angle. This is one angle, this is the second angle, and so on. And because it's a right triangle, then from geometry we know this is also a right angle, and that goes the same for all of these. So inside we also have a square. Now let's find the area of this square in 2 different ways. So one way is we know that each side has length AB, so the area will be A plus B squared. And the second way is we can find the area of these 4 triangles and add it together with the area of this square. So let's do that. So the area of one triangle is going to be 1/2 AB squared. But we have 4 of them, so it'll be 4 times 1/2 AB. And we're going to add the area of this square inside, so that's going to be C squared. And now let's just do some algebra to finish the proof. This distributes into A squared plus 2AB plus B squared. And over here, we'll get 2AB plus C squared. And of course, we can cancel these out. And we get A squared plus B squared equals C squared. And that concludes the first proof. So let me label it again, A, B, C. But here there's one crucial step that we're going to be using, which is we're going to split by the hypotenuse. Let me see if I can get this right. And so now we have split in the triangle into two triangles. And we're going to label this one H. And also, I forgot to do this earlier, but I'm going to split each of these sides and label them accordingly. So I'm just going to call this side, which begins here, C2, and this side C1. And from that we can see that C1 plus C2, we're going to define that as C. So when we'll get a squared plus b squared equals c squared in the end. Okay, so let's start. This method relies on similar triangles. So here, let me get a different pen. I'm gonna label each angle so we know. This angle right here will be 1, and this one will be 2. This one will also be 1, and this one is 2. And of course, these are all right angles. Okay. So, because these two triangles are similar, we can compare and construct ratios from their sides. We'll now do hypotenuse divided by short. So here we have A, which is the hypotenuse of this small triangle, and we'll divide it by the short side, C1, right here. And this ratio is going to be the same as the hypotenuse divided by the short side of the big triangle. So the hypotenuse is going to be C, and the short side is A. Similarly, we can do the same thing. We'll do hypotenuse divided by long, but for the other triangle now. So the hypotenuse of this triangle is B, and the long side is C2. And this is going to be the same as the hypotenuse divided by the long side of the bigger triangle, which is going to be C divided by B. And now we can do some algebra, some rearranging, and get this. A squared equals C times C1. B squared equals C times C2. And now we'll just simply add these two equations together and finish the proof. So here we'll get a squared plus b squared. That's equal to c c1 plus c c2. And this right here, if we factor this out, that's equal to c times c1 plus c2. And of course c1 plus c2 is just c, so this is c squared. And that concludes the second proof. I'm going to label it something else this time. So here at the bottom we're going to have A, and this I'm going to call X, and this I'm going to call Y. So really we're going to prove A squared plus X squared equals Y squared. And here I'm also going to add a slight edge. I probably should have drawn this a little better, but it's okay, I think. And I'm going to draw a line right here. So Y really should be this length up to here. So I'm going to call this also Y. Okay. Then what's really happening is we're going to shift this x value a little more, and we're going to see what happens to y. So we're going to do a small change dx, and that's going to correspond into a small change of y dy. And let me make this a little bit bigger. So I'm just going to zoom in on this portion right here. So here we have dx, here we have dy. And we can see in the infinitesimal limit, as dx is smaller and smaller, then this angle right here is going to start looking more and more like a right angle. And from that, we can conclude that these are similar triangles once again. So if we draw this angle and this angle, so that's right here, we'll see that because this is a right angle, then this is the first angle. Of course, this also is a right angle, and this is the second angle. So in the infinitesimal limit, they become similar triangles. And then we can, of course, do ratios. So it's going to be hypotenuse divided by short. But you can't really see that it's short here. But that's what it's going to be. So this is the hypotenuse. And we'll have dx divided by dy is equal to y divided by x. And this right here is a differential equation, and we can of course solve it by separation of variables. So here I'll put y dy is equal to x dx. We're going to integrate both sides, and from this we'll get y squared over 2 is equal to x squared over 2 plus an integration constant. And we're just going to simplify this by multiplying 2 on both sides. 2 will be absorbed into the constant, so we'll just get y squared equals x squared plus c. And we're almost there, but we just need one final condition. So if you imagine what happens to y when x gets smaller and smaller. So if we make x 0, or get infinitely close to 0, then y starts to approach a. So we can actually say, as a condition, we have if x equals 0, then y equals a. And of course, with this, we can solve the equation. By plugging y equals a, we'll get a squared, and x equals 0, 0 squared plus c. We get c is equal to a squared. And this, of course, leaves us with, Pythagoras, his equation. And that concludes the final proof.